Good morning. Today also we will talk about crystal defects in metals. Last couple of classes we introduced the concept of point defect like vacancy, interstitial atom, substitutional atom. We also looked at the effect of temperature on concentration of vacancy. We also looked at length about line defect, that is dislocation, which is a boundary between deformed and undeformed region or slipped and unslipped region. We talked about two basic types of dislocation, that is edge and screw. We also looked at the nature of stress field surrounding the dislocation. And today we will talk about a part of this dislocation interaction. We will also look at a defect, surface defect called stacking fault. And to sum up, we looked at two types of dislocation, that is edge and screw. If we look at their characteristic, which is listed here, these are certain features of edge dislocation. This is the certain features of screw dislocation. In fact, when you look at a dislocation, so basically you have to define two things. One is the dislocation direction, and another you also need to define the Berger vector. This is B. Say suppose this is the unit vector representing the dislocation direction t, and this is the Berger vector, and angle subtended is theta, then clearly this is a mixed dislocation and it has an edge component which is like this B sin theta, and this is the screw component which is B cos theta, it's Berger vector. Now, clearly if it is an edge dislocation, say suppose if it is an edge dislocation, means this is the dislocation direction, this is the Berger vector, it can slip only on the plane which contains both T and B, and therefore, the slip plane is given by this B cross T. Now, same thing if you try and do for screw dislocation, this is the dislocation direction, this is the Berger vector. So, if you take a similar thing, this n comes out to be that the plane, it comes out to be 0. B cross T is actually the vector representation of the slip plane. So, in this case n comes out to be 0, which means this is more mobile by glide. It can pass through, say suppose if there is a dislocation, say suppose here this is one plane, a screw dislocation moving, it meets an obstacle here, it cannot go beyond this, and at that time say suppose if there is another in slip plane like this, there is a possibility it can move on this. So, this movement is known as cross slip. So, which is listed here. So, if you look at this, then the dot product between B and T, so in this case the dot product is B itself, here it is 0, and you look at the stress field. Stress field, so basically if you assume the dislocation to be aligned along the z direction, if this is direction x 1, this is direction x 2, and your dislocation is line is along x 3. In that case, it was shown that if it is an edge dislocation, it will have these component of stresses, if it is screw, it will have these. So, look at the two, here these two are 0, whereas here each of these for screw dislocation, each of these component is 0. So, together if you have a mixed dislocation, you can say that all the 6 stresses will be 6 component of stresses will be present. We also estimated the elastic stored energy in the dislocation, and which comes out to be of this order, and this nu is actually Poisson ratio, and we know for most metal this is around 0.3. So, we can say on a rough say edge, maybe edge dislocation has a little more stored energy, elastic stored energy than screw, but for all rough calculation to understand dislocation interactions, we always assume that this is an energy of a dislocation is around say 0.5 g shear modulus B square. For many cases in the metal the g is constant. So, B square is directly gives a measure of the elastic stored energy of the dislocation. Dislocations having high or large Berger vector will be unstable. This is the reason why some of the you can try with some of the ceramic crystals or say sodium chloride crystal. If you look at that structure, there the Berger vector is much larger than the Berger vector that you get in metallic materials or metallic crystal. Now, about dislocation movement, we said that primary movement is glide through slip, both edge and screw can glide, but screw dislocation and glide not only on the present slip system, it can cross slip onto another slip system also, which edge dislocation cannot do, but edge dislocation has another type of movement, which is through interaction with vacancies. Edge dislocation means it is an extra plane of atom, and if a vacancy from lattice diffuses here, then the dislocation can climb up, or else if the dislocation climbs down, it will generate vacancy. So, that means this is the type of motion which is known as non-conservative motion. With this background, we also calculated the force that acts on a dislocation, and this is if you try and recollect, if this is a crystal, this is the slip plane where you have a dislocation, and this dislocation line is aligned along the direction, this is x 1, along the direction x 1, and you apply a shear stress tau, and in this case simply we could calculate the force on the dislocation, which comes out to be shear stress on that particular slip plane times the Berger vector. This you can say, this is, for example, we can always say that this is the resolved shear stress times Berger vector is the force on the dislocation. So, this is the force which is responsible for the glide motion of the dislocation. But in a more general case, often it is not the state of stress or the elastic stress field can be much more complex. In that case, in a more general case, how do we find out, which is shown over here. In a more general case, if you have all components of the stress field to be present, so that means there are all 6 components of the stress field. The stress matrix is actually symmetric, we know there are 6 component of stresses, and which is represented as a 3 by 3 matrix, that is sigma. So, this is equal to sigma dot B, it is a vector, although it is a dot product, but it is a dot product with state of stress which is at second rank tensor, and so therefore, this is also a vector, and if you take a cross product with the dislocation direction. So, this is the force acting on the dislocation. Now, in this particular case, what is tau? Tau is the shear stress acting on the plane which is intersecting the x 3 axis. So, that means it is acting along the direction x 2, this distance is x 2. So, therefore, tau is represented as sigma 2 3, whereas here the dislocation is aligned along this direction, along x 1. The dislocation is aligned along x 1. So, that means this vector representing the dislocation direction, we can say it is 1 0 0. So, that means T 1 is non-zero, rest are 0, whereas the Berger vector is pointing, if we assume this is an edge dislocation and Berger vector points along the x 2 direction. So, therefore, only the x 2 component of the Berger vector is non-zero, rest are 0. So, let us see, I mean, how can we do find out this force on the dislocation as taking this as a more general case. Now, here we will introduce, it may be better if I introduce a concept called this is repeated subscript as or Einstein or a Cartesian tensor using the Einstein convention of a summation, and which is shown over here. To be more explicit, what we can do when we have to find out a cross product, say basically say suppose if we do a cross product of two vectors B cross T. Now, this vector, I mean this can be represented as that cross product P can be represented as, we introduce another tensor epsilon I j k and we multiply this by j and T suffix is k. Now, here what it means, if there is a repeated suffix, it means summation over j and the j changes from 1 to 3 in a Cartesian system. Similarly, there is a summation over k as well. So, k also changes from 1 to 3 and this tensor epsilon I j k. So, this is a tensor of third rank and I j k can have values 1, 2 and 3, and this is equal to 0 if any two of this suffix they are equal. Any two, if they are equal, then this is 0, and if this is in this sequence 1, 2, 3 or epsilon 2, 3, 1 in this sequence, then it is plus 1. If it is in the reverse sequence, say suppose you imagine, so this is 1, 2, this is 3. If it is 1, 2, 3, 3, 1, 2, 3, 2, 3, 1, 3, 1, 2, if it goes in this sequence, then it is plus 1. So, that means, if it goes in this sequence, then this this tensor, this its magnitude is plus 1. If it goes in the reverse direction, that means 1, 3, 2, epsilon 1, 3, 2, then this is equal to minus 1. Now, with this, if we apply that here, and then we in that case this product sigma dot B cross T, this will be represented as F I, this is the ith component of the force. It can have 3 component along 3 direction, x 1 axis, x 2 and x 3. So, I represents that component, and this is equal to epsilon I j k, this is a tensor of a third rank, then sigma j L. So, sigma j, so there is a summation over j here, and then sigma j L dot B. So, here you have B, we use suffix L. So, that means this sigma j L B L, where the suffix L is repeated, L can have value from 1 to 3. So, that means this represents this dot product sigma dot B, and then you have T k. Now, here look at, you know, with this convention how simply the calculation can be done. Now, in this case only the B 2 component is non-zero, B 2 which is equal to B. So, we write here, so L can be have value only 2. Similarly, the suffix for T can be only 1, because the T 2 and T 3 both are 0. So, most of these they are fixed, this is 1, this is 2. So, therefore, if this is 2, this component L is 2, we write 2 here. In that case, we know if this is a dislocation, if it is 2, then let us see that what can be the value of J. Now, J here, this sigma, you see only 2 3 is existing. Now, if 2 3 is there, sigma 3 2 is also there. So, what we can do, because sigma 2 3 is equal to sigma 3 2. So, that means stress tensor is symmetric. So, this expression, this is 3 2. So, then only unknown here suffix is I. Now, what can be the value of I? Only number which is left is 2. So, 2 3 1 is equal to plus 1. So, therefore, here you can see straight away this will be sigma 3 2 B. So, sigma 3 2 is tau. So, you get exactly this expression. Now, why we did it at length? Because we have to look at interaction between two dislocations. Say if we want to find out how well a dislocation will interact in presence of another dislocation. Now, in this case what we have to find out, look at the stress field of one dislocation and how it is going to react with the stress field of the other. So, which is shown over here. Say suppose we consider two parallel screw dislocation with a parallel Berger vector. So, here this dislocation lies along the axis x 3 here, and we say that on this another dislocation is here which is also lying along x 3. Now, this interaction, nature of this interaction will obviously depend way these dislocations are arranged, and therefore, this we take a very simple example here, and we know the stress field of this dislocation. We know that this is the stress field, these are the 0, these stress components they are 0, only non-zero stress component are this, and since stress tensor is symmetric, this is equal to this is equal to that. And here this Berger vector is represented, is also lying along the direction x 3. Now, let us say the Berger vector of this is 0 0 b. So, this is along x 3 direction, and this dislocation direction is also parallel to x 3. So, this is also 0 0 1. So, therefore, you substitute back into this expression, then you get this is B 3 T 3, only these are the two non-zero. So, obviously, there are not many choice. So, you have two components F 1 and F 2, and we have taken this Berger vector, say suppose one is B, another is B prime. So, let us say that this is B prime, or vice versa. So, in that case you can substitute, go back and look at the stress field expression, and if you substitute you get an expression like this. What does it say? So, what it says that F 1 is positive if B 1 and B 2 they are both positive, the similar dislocation, then F 1 is positive, that means force along this direction is positive. Similarly, force along F 2 here along this also is positive. So, that means the force is acting along this direction and along this direction, which means you can convert it into cylindrical coordinate also, which can be done very easily. Say if you take that, okay, if we say that my this distance is r, this angle is theta, then you just substitute x 1 equal to r cos theta, then x 2 equal to r sin theta. If you substitute that, in that case you will find that the force along this direction, force along that radial direction, this is the only existing force, this will be G B B prime over twice pi over r. So, this expression is so simple, and what it shows that if the dislocations are alike, both have similar character, they will repel each other. But if one is a positive, another is a negative, then the force will act, say B equal to minus B, B prime equal to minus B, then the force will act in the opposite direction. So, basically they will attract each other. So, that means if you assume one is a right handed screw, another is a left handed screw, if these two dislocations come and meet together, if in that case the dislocation will disappear. So, this is one way in which a dislocation can disappear as well. So, this is what we talked about. If we have two parallel dislocations which are alike, in that case they will repel, and this is a case where these dislocations, one is a right handed screw, another is a left handed screw, then there will be a force of attraction and they can come together and annihilate one another. Now, similar calculation in case of a edge dislocation will be also can be done in the exactly the same way, following the tensor Cartesian tensor convention I just introduced, and it is very easy to understand nature of this interaction, and which is shown here in this slide. And here also the nature of this interaction will depend on whether they are parallel to each other, whether the Berger vectors they are also parallel. So, that means this is a case where parallel edge dislocation with parallel Berger vector. You can do in exactly the same way if they are parallel dislocation, but Berger vector is at right angles. These are some of these exercise which you can try yourself, and with the way it is introduced, it should not be difficult for you to arrive at this and understand such interaction. Now, in this particular case edge dislocation, the non-zero component of stresses which are listed over here, and here again the Berger vector is along x 1 direction. So, unlike that where the Berger vector was along previous one along x 3, here Berger vector is along x 1 direction. So, B you can represent at B 0 0, only B 1 component is a non-zero component. Similarly, in case of the T, it is only the x 3 component is non-zero, and with that if you subtract and substituting, let us say find out a general expression for the ith component of stress F I. So, you will write this is the overall general convention. Now, here T only non-zero component is T 3. So, you have only T 3. So, that means K can take value 3. So, replace here 3, here 3. Similarly, B can have only value B 1. So, B 1 and here also that is L is 1, here also it is 1. Now, you left with only two suffix I and J. I of course, it will denote the ith component of stress. So, you will find out whether I is 1 or I can have value 1, 2, 3, 3 component of force. Now, what value can J have? Now, here this J, it will depend which are the non-zero component of stress. So, J can have value, this is already 1. So, J can have value 2 because sigma 1 2, this is a non-zero component. So, J can have a value 2. Now, can it have value 3? If you put sigma 3 1, look at this table here, sigma 3 1, it is 0. So, it cannot have value 3. So, you substitute, but it can have value 1. So, j can have value 1, this is sigma 1 1. So, you have two possibilities sigma 1 1 and sigma 2 1, which is substituted here. So, this gives the ith component of the force. Now, clearly there are two value I can have. Now, if I, can it be 1? Now, it cannot be 1, because I, if we say that if it is see I can have 1, because here second part here, if we put I equal to 1, in that case this becomes 0, because epsilon 1 1 3 this is 0. So, this part becomes 0, but here epsilon I 1 2 3 this is equal to 1. So, therefore, F 1 will be equal to epsilon 1 2 3 sigma 2 1 B 1 T 3, and you substitute, look at that value of the stress field and substitute here, you get the force F 1. So, F 1 is the force acting along this direction, this is non-zero. Now, similarly, can F this I be 2? Now, here if you substitute I equal to 2, look at here, if you put I equal to 2, in that case this coefficient epsilon 2 2 3 this is 0. So, this vanishes, but here 2 1 3 remains. So, now 2 1 3, look at here. So, if you look at the sequence, it is just the reverse sequence. So, we talked about this 1 2 3, we said that epsilon I j k is positive plus 1 if this suffix I j k are in the clockwise sequence 1 2 3. Now, if it is 2 1 3, then in that case that means 2 1 3, in that case this is minus 1. So, if you substitute here 2 1 3 minus 1, then you get this expressions. So, there are, so now only two component of force will be acting here, one is along this direction which will help it to glide along this, whereas there is a force along this direction which this is not a slip plane, this is the plane on which it can climb. So, basically, so this will be ineffectual, I mean this cannot contribute to the glide movement of the dislocation, but it can certainly help in climb motion. Now, here also if you look at this, let us look at the nature of interaction depending on where these dislocations are located, because this force is clearly a function of, because what we can say these are virtually constant, because we know that Berger vector in a face centered cubic crystal, the Berger vector they are fixed, this will be, so these are all constant. So, nature of this interaction depends only on the location of one dislocation with respect to the other. So, that means the relative positions. So, that means the coordinate x 1 x 2. So, this is, and x 3 does not feature here. So, that means along the length of the dislocation, the nature of stress field is exactly same. Now, here also if you do this polar that conversion, which is easy to understand. So, you can do the same thing and show that this expression looks much simpler. So, this is inversely proportional to the distance between the two dislocations. So, that means if the dislocation is far apart, interaction will be less. Now, let us look at this coordinates, say this is a 2D diagram, this is x 1 axis, this is x 2 axis. These are lines where x 1 is equal to x 2. If x 1 is equal to x 2, what does it show? Let us look at the nature f 1. If x 1 is equal to x 2, then f 1 is 0. So, that means if a dislocation lies here, there is no glide force. So, this is, you can say, one position of equilibrium. So, that means this point, say suppose we take a section here and let us try and understand what is the nature of the force as you move from this point to this, or you come from a distance along this up to this. Now, here clearly here you will have the force is equal to 0, and if you look up here in this case, this force, you look at it, x 1 is greater than x 2. If you are here, x 1 is greater than x 2. So, F 1 is positive. So, therefore, the nature of the interaction is one of repulsion. So, it is repelling. So, it is not like screw dislocation that exactly the nature of the force, it can change from repulsion to attraction, even if they are of have similar character. Even if they have similar character, they can change over from repulsion force to an attractive force depending on where these dislocations are located. So, here this is a position of equilibrium. If you go this side, there will be repulsion, but if you come here, in that case x 1 is less than x 2. So, therefore, the F 1 is negative. So, it is pointing towards this direction. So, if a dislocation is located here, there is a glide force and you do not need much of a force to move a dislocation. So, dislocation will glide along this, and when it comes over here, in that case here x 1 equal to 0. So, F 1 equal to 0, and here if you try to push it here, then you will find that force is acting in this direction. So, again this will bring it here. So, this is a position of most stable dislocation configuration. If you displace it here, it will try to come back to its disposition. If you displace it this way, again it will try to come back to its position of that equilibrium position. So, this is a very stable configuration, whereas this is an unstable position of equilibrium. Displace it slightly here, this will move this direction, and if you displace it slightly this, then it will come here. So, this is an unstable equilibrium. So, if you do that and make a plot, you will get a plot, say something like this. F is negative, very close, when this in this portion F is negative, here F it is 0. So, this point represent this, again it goes up and then it will go to a distance somewhere, you can find out where it will be maximum. So, basically where it will be maximum at which position of theta or which position of, so basically here we say that x 2 is fixed, at which value of x 1 this will be maximum. You can differentiate and find it out, and you will find this is the maximum distance. This is the distance where F 1 is maximum, and this will be symmetric on the either side. Now, so we have understood so far that since dislocations, they have their own stress field. So, if one dislocation comes close to another, in that case the elastic stress field, they will interact with each other. Now, suppose what happens when a dislocation, crystals have several dislocations, and say suppose this is a slip plane in the crystal, you have an edge dislocations. Now, there will be several dislocations which will be threading like a tree, say basically threading through this slip plane. This is perpendicular to the slip plane. This is an edge dislocation. So, basically we say that when a dislocation will move in a crystal, it is bound to come near other dislocations which are intersecting the slip plane. So, what happens when such a dislocation, you apply a stress field here. So, there will be stress force here on the on these dislocations. When it is moving on this plane, this will try and move on this plane. So, when they interact, what happens, which is shown here. When it comes this side, this will, its Berger vector is like this. So, what will it do? It will create a step over here. So, look at this is the step over here. So, here also similarly this dislocation will also develop a step like this. Now, look at what is the Baja vector. In this particular case, the Baja vector is pointing along this directions, and what is the dislocation direction? Dislocation direction is like this in this part. So, this portion of the dislocation, it has a this portion of the dislocation has an character is little different. This part, this Baja vector, if this is the Baja vector, this is the dislocation direction, this is at right angle. So, this is edge. So, this also is edge, but this is a screw dislocation. So, the screw dislocation can move, it has a multiple, you can cross slip, it can move on any plane which contains it can also move in this plane. So, this is the type of step which you can say is a mobile, it can move along the length of the dislocation and come out of the slip plane. So, same thing here also, its character is that of a screw dislocation. So, this type of step is called kink, and it has a screw character, and it can move along the length of the dislocation. Now, what happens if these dislocations are little different? Now, in this particular case, this is an edge dislocation, this is a screw dislocation, this is the Baja vector along. So, now here if it moves, it passes through, then what happens? Say this goes this side, this comes this side. So, here this will try to push a part of this dislocation on the upper plane. So, this moves to the upper plane. So, now look at it, this dislocation still lies on the previous slip plane, whereas this dislocation has moved to a plane just above it. So, they are no longer on the same slip plane, and here is another dislocation which is like this here, and what is its character? Baja vector is this. Baja vector remains same along the length of the dislocation, it does not change unless another dislocation meets. So, basically here, so here also it is perpendicular. So, this also is has an edge character. So, this type of step is called a jog, and this jog, if it is a slip plane, it can move on this perpendicular plane perpendicular to this. But if you look at, say, suppose a face centered cubic crystal, in a face centered cubic crystal, the slip planes are not normal to each other. Slip planes, say if it is a one slip plane which is 1 1 1, the another slip plane which also has to be 1 1 1, that will intersect at an angle. So, if a jog forms here, if there is a perpendicular dislocation, if a jog forms here, then that jog will not lie in a common any 1 1 1 type slip plane, which is a normal slip plane in FCC. So, this will act as a obstruction to the movement of the dislocation, and this jog dislocation can nevertheless move if vacancies can migrate to this jog. Then this portion will move in a non-conservative manner, whereas this will be the normal glide motion. There are several interesting dislocation interaction that can take place. If we consider, say, let us say, if we consider face centered cubic crystal, say a dislocation moving in one slip plane, if it comes and meets another dislocation along a line where the slip planes meet, which is shown over here. This is a plane 1 1 1. Here is a dislocation, although I have represented it by an edge, it is not necessarily an edge dislocation. We can consider, say, suppose this is a mixed dislocation. So, although I mean just to represent it, it has been done like this, and if it is moving along this, it comes here. Another dislocation whose Baja vector is this is also moving along this, and when they meet together, what happens? So, what we can write? So, that means two dislocations, say if B 1 and B 2 they meet. So, they will vectorially add up and produce another dislocation with a Berger vector B 3, and this will be energetically favorable if we check B 1 square plus B 2 square, which represents the energy of the reacting dislocations, the two dislocation. If this is greater than B 3, the product dislocation, then this is energetically favorable, this reaction will take place. And when this dislocation reaction takes place, this dislocation will lie along the line of intersection. That means, suppose say this is plane, suppose this is the plane 1 1 1, and this is the plane, another plane, say the bottom one, this is the plane, let us say another 1 1 1 plane, say let us say 1 bar 1 bar 1, another plane, and they meet along this line B D. So, a dislocation which is here moving along this, and a dislocation which is moving in the bottom plane B C D, and they together they meet here. So, then the two, when they react, the dislocation line will lie along B D. So, which is shown here, this is dislocation which is lying along this direction, which is perpendicular to this plane, say suppose it need not be perpendicular, this is a tetrahedron. So, this is the direction, that is line of intersection of two 1 1 1 plane, it is lying along this. So, this will have a Berger vector which you can calculate, and then if they are not along this, so that means if it is a mixed dislocation or an edge, then it will have a specific slip plane which can be calculated. And if you find that this slip plane is not the normal slip plane, say suppose if it comes out, the plane on which this dislocation line and the Berger vector lie, this is lie on this particular plane, which is not a slip plane, then we say that this is a dislocation lock. And this type of dislocation lock, two perfect dislocation moving on two intersecting 1 1 1 plane, if they interact, they develop a dislocation lock which is immobile, and this will not allow. So, this will have a stress field surrounding it. So, once this lock is formed, this will not allow the other dislocation to pass through this, this will have a stress field, this will repel, they will stop here. The other dislocations will not be free to move. So, this is the way a crystal hardens during the plastic deformation, and which is shown over here. So, these are the two planes, this is 1 1 1, this is 1 bar 1 bar 1, and you can write down the Berger vector of this, calculate the Berger vector of this particular dislocation A by 2 1 0 1 bar, which is shown over here, and this is A by 2 0 1 1, which is shown here. If the two add up, then this is the Berger vector of the resultant dislocation. Now, here you can clearly see, if you find out the energy of this dislocation is A square over 2. This is also so, this type of dislocation, if you try and check whether this dislocation is energetically favorable or not, and what it will find out that this dislocation is A square by 2, this is also A square by 2, total energy is A square, whereas this dislocation energy is A square by 2, which is certainly less. So, this is energetically favorable. So, this reaction will take place, and this, and you can then find out what is the line of intersection. Line of intersection of these two plane is 1 1 bar 0. If 1 1 bar 0 and this is 1 1 0. So, this character, this is an edge dislocation. The Lohmer lock which forms, this has an edge character, because this is perpendicular to this dislocation direction. Berger vector is perpendicular to the dislocation direction, and on which plane does it lie? Clearly, it is 0 0 1. So, which is not a common slip plane in the face centered cubic crystal. So, this acts as a dislocation lock. So, this dislocation will inhibit further movement. Once this lock is formed, this will inhibit further movement of dislocations on these planes. So, this is one mechanism of strain hardening dislocation mechanism, which explains strain hardening behavior of face centered cubic crystal. Now, we will let us look at the way the atoms are arranged and depending on that arrangement of atoms is there any other types of dislocation that we can think of. So far dislocation that we have considered is something like this. This is a close packed plane of a face centered cubic crystal. So, all these atoms they are closely packed and these directions are, this is a 1 1 1 plane and these directions are 1 1 0 direction, these are diagonal face diagonal direction. And the next layer which will go and occupy the one of these sites. If you look at, there are two sites, if this is a layer A, this is a site B, this is site C, and when the next layer comes it occupies let us say B site, but it blocks the C as well. Part of the C is also blocked and it cannot occupy the C site. C site is this site, and then when the next one goes it occupies C site. So, face centered cubic, this is the way the dislocations are arranged. Now, what happens if this sequence is disturbed? In face centered cubic crystals, these planes 1 1 1 planes are arranged in sequence A B C like that. Now, what happens if this is disturbed, which is shown over here. Now, look at this here, say this is the A site and now suppose that the B layer has also been put. So, these are the B site. Now, what happens if from this is the B site. So, B site it has to go from here to here. So, this atom, this layer earlier was occupying this. Had it occupied this, if you draw the circle, you will find this will touch this as well. If we draw the same circle, you will find that this will touch this as well. Now, if this moves from here, that means next row of atom, if it moves here, then what happens? A gap is created. And a gap is created, and thus that means this is a line type of a line defect. There is a gap is created on this particular plane, and so this is a dislocation. There is a dislocation here. A dislocation is created here, and also over A here the sequence also breaks. After A, this is the C, whereas this part after A the sequence is B. So, in this on the two sides of this defect, the sequence, the way the 1 1 1 planes are arranged, that sequence is disturbed, which is very easy to understand. And is this energy variable? And this is to understand that, imagine visualize like this, you have an atom here. Now, you have two sites here. If you take a hard sphere, put this atom here. Now, next layer of atom, if you put it here, the next one immediately you will not be able to put in that position. You have to see, this is a site here immediate. So, this is one side, this is another side. So, here you cannot put, if you put it, it is coming here. So, part of this site is blocked. So, similarly, here also you can't put, you will not be able to put an atom. If you put, it will come here. So, that means let us say if this is a B site. So, now if a B site, a perfect dislocation, it has to move from this position to this. this is B site, this is the next B site. So, this is Berger vector 1 1 0. Now, that means what it has to do, this atom will move up the plane and again come down, which is little difficult energetically. Whereas, what it can do, it can pass through the valley like this and come like this, and this is what has been done in the figure which I had just shown. So, you look at this figure here, this is what has happened. This row of atom was earlier touching this, occupying B site, this has moved to C site, and it creates a dislocation, a defect over here. And in that case, so look at what is this, it will be interesting to recall what is the packing sequence in a hexagonal closed packed structure. This is called hexagonal closed packed structure. Here what you have, the C layer is not occupied, the sequence is A B A B A B, that is the way. So, here you can see through, you can see that that background color, this background color is visible here. So, that means this layer is not occupied. So, therefore, and let us see what has happened over here. If you look at this, this is the way these dislocations there, I mean these atoms are arranged in the closed packed 1 1 1 plane. This is the closed packed direction. I will leave it to you to find out the dislocation direction, which is written over here. And then what is this direction? You will find out that this direction is a direction of 1 1 2 type direction. So, basically this direction is a 1 1 2 type of direction, and here what we have done is, say suppose this is the Berger vector, which is A by 2 1 bar 1 0. This splits up into 2 Berger vector, say part of the crystal is this, part of the another side there is another dislocation. So, this is a perfect dislocation, which is this we call perfect dislocation, because it does not disturb the packing sequence. Whenever this type of dislocation is there, then the packing sequence remains intact. But when you have this kind of a disturbance, this splits into 2 1 1 2 type of dislocation, and you can find out the magnitude. Magnitude will be A by root 6. And once you do this and then you find out the energy, you will find that the energy, there is a reduction in energy. So, therefore, this dislocation is energetically favorable, and using that hard ball concept also, it is apparent that this kind, when this atom moves through the valley, the movement is easier. Now, let us look at what happens. So, this is a picture. What happens? Say this is A, this is B, red is B, red is B. A part of this dislocation has taken C layer. So, and here, then here there is a gap. So, you have a dislocation here, you have a dislocation here. So, these are the partial dislocation which is shown over here. These are the two partial dislocations, and say suppose somewhere here this side that they may join together. So, this may be a perfect dislocation which is shown over here. So, this is a perfect dislocation, this part the stacking sequence is not disturbed, or whereas here the stacking sequence is disturbed. So, only in this part, the stacking sequence, there is a disturbance in the stacking sequence. Now, this type of fault where the stacking sequence is different is called stacking fault. So, this is a this has two dimensions. This fault exists over a particular area. So, this has a 2D, 2 dimensional. It has 2 dimension, it has length, it has width, and this width of this, you can say that these are the distance between the two partial dislocation, and this will be very easy to calculate from the dislocation interaction. In fact, we can approximate this. In this particular case, we can approximately say that the force acting between the two is equal to G, the dot product of these two Berger vector over this, and this is equal to, because it creates a new defect which is called stacking fault energy. This is as if a new surface, visualize as if a new surface is being created, and whenever a new surface is created there will be an energy associated with it, and we call this energy stacking fault energy. And it is possible to calculate the stacking fault energy. We will see later how dislocation you can see in a microscope, in a transmission electron microscope, and these partial dislocations can be seen, and if you can find out the distance between the two partial, it is possible to calculate the stacking fault, estimate stacking fault energy. To sum up, it is something like this. This is the type of sequence A B C A B C. This is the perfect, I mean where there is no stacking fault, and whenever, suppose this particular case here, this part of the crystal, it has gone through, moved through one partial dislocation, that is A by 6 112 type, which is shown over here. So, in that case the B moves to C. If B moves to C, C will move to A, C will move to A. Similarly, and this sequence continues in that direction. So, look at over this, you have A B C A C. So, you can see here it is C A C. So, here the sequence is something similar to a hexagonal closed package. The sequence is disturbed. So, therefore, we call this a stacking fault, and it consists of two partial dislocation. So, one is a leading dislocation, this is a trailing dislocation, and we say that this has here the stacking fault, there is a disturbance in stacking fault, and we call this as a 2D or surface defect. And next class we will build upon that importance of it is quite important to know the behavior, deformation behavior of face centered cubic crystal is strongly dependent on the type of that stacking fault it has. And say for example, the cross slip will become more difficult if the stacking fault energy is low and these partials are far apart. So, unless these partials there is a constriction, they will not be able to move, I mean cross slip. So, this adds also to the strain hardening, affects the strain hardening behavior of face centered cubic crystal. Thank you.